Yeah, before me, Jane gave an excellent talk, giving the review of mostly the solar type, like sun, solar type stars, and also she actually included all the major physics that are, so she talked about all the major physics that need to be included in any stellar structure and evolution code. But for my talk, I am mostly interested in the more massive stars, which are almost 80 to 100 solar mass or 150 solar mass stars. And for them, two more physical physics that would be more important, and that is the convection and overshoot mixing, and also the mass laws. So I'm going to touch upon those two physics as well. So here for today, I'm going to talk on the new mechanism for the origin of WNL stars, and this mechanism that we call as the exposure of fossil convective cores. And it has been done in collaboration. I was a postdoc at Australian National University in collaboration with Mark Krumholz, Ralph Sutherland, Alexander Hager, and Michael Arpita. Okay, so the first question is like, why? There are very few people who are interested in massive stars, but then why massive stars? Even though massive stars are less in numbers compared to their low mass cousins, but still they are the primary sources of ionizing photons, chemical yields, and mechanical luminosities. And but then why not only just stellar structure and evolution physics, but also if you look at other areas of astrophysics like say, cosmological simulations, galaxy formation and evolution, how does the stellar evolution models goes into the picture? So to understand the ionization history of the universe or chemical evolution of galaxies over cosmic time, we need very fine-tuned stellar evolution models. And these models, the inputs from these models goes into the population synthesis codes, and then those outputs actually goes into the galaxy formation or evolution simulations, which is a subset of kind of cosmological simulations. So for realistic estimates of be it ionization history or the ionization evolution or the chemical evolution of galaxies over cosmic time, one needs to understand the structure and evolution of massive stars. But then there are some existing stellar tracks, and they're doing pretty good job since quite some time. It's more than a few decades, and but due to computational resources at that time, because they are in 90s, and due to the restrictions of the computational resources, these stellar tracks have certain limitations, and for that reasons, even the population synthesis models that use those stellar tracks are also they also have certain limitations, and that's why you need some new stellar tracks. And coming to the new stellar tracks, what are those limitations that makes us go towards the new stellar tracks? Now the most popularly used code is the Geneva code, and I can see even in the Zoom list, Georges is there, and this I have taken from their webpage, and you can see if you look at their metallicity, they go to the least metallicity is 1/10 of solar metallicity, not below that. But if you look at to understand the high-Z galaxies or the metal core environments, you need stellar models which are lower than 1/10 of solar metallicity. But there will be the questions like, we don't have probably the mass law schemes, but if you look at the mass law schemes that are existing, or in MESA, those are the Dutch mass law schemes for the massive stars. If I talk about the O stars, we have the Ring mass law schemes, Ring 2001, which goes to 1/100th of solar metallicity. So probably we can at least go till 1/100th of solar metallicity, if not below that. And now the next part is like, what are the different mass resolution? So now if you look at this left side is this Mene and Meda paper, 2000 paper. This is very famous paper, and this is at solar metallicity, and they have tracks for this is the HR diagram. They have tracks for rotating and non-rotating cases. And if you look at the higher mass regime, you can see that they have only 3 masses, that is 40, 60, and 120 solar masses. And later on, this Geneva track, which is like Georgi et al. 2013, we can see that they have several other rotation rate cases, although in the high mass regime, the mass resolution between 60 to 120 solar mass, they have only one more massive star, which is like 85 solar mass cases. But if we look into their evolution, and I'll show right within some time, but they don't move they don't move on the HR diagram very similarly. So probably interpolating between them wouldn't be probably that much right choice to have accurate luminosity or effective temperature budgets. And also because these are the parameters that ultimately determine what would be my ionizing photon luminosities and also the chemical yields and etc. So now the next step is what goes into the population synthesis code. The most widely used population synthesis code is Starbus 99, and that uses these Jennifer tracks and also the atmosphere Potsdam-Wolfrath atmosphere code. And what they're saying that normally for although these Jennifer tracks, they have several rotation rates values, but this Starbus 99, they use only 2 rotation rate cases, which is almost non-rotating and 40% of the breakup velocity, or which is like V by V greater 0.4. So now the question is like, and they're saying that they're expected to bracket realistic rotation velocity distributions in stellar populations. But there are observations like at low metallicities that, and also the theories of star formation theories that suggest that probably the stars are rotating at velocities V by V grit is greater than equal to 0.4. So there can be even rapidly rotating stars as well. And also, like if you try to, if you don't have the final velocity resolution and try to interpolate between non-rotating and 0.4 V by V theta 0.4, then there can be errors associated in the estimates of the ionizing photon budgets, chemical yields, and mechanical luminosities, etc. Not the mechanical luminosities much, but definitely the ionizing photon budgets. And so that I'll talk about it pretty soon. And now let's look into the existing and very recent this MIST track. This is MIST 1 solar models and tracks, and you can see that in the high mass regime, for me, high masses are mostly 60 solar mass onwards. So if you look at this high mass regimes, like not the very massive stars, not the VMS again, that is 150 solar mass and beyond, but it's mostly 60 to 150 solar mass that I'm interested into. So you can see that 70 to 150 solar mass stars, if you are rotating and non-rotating, they are going in 2 different directions on the HR diagram. So they have completely different kinds of luminosities and also the effective temperature. So if you try to estimate your ionizing photon budgets from them and then try to interpolate to figure out what would be the ionizing photon luminosity budget for the rotation rates, which are in between non-rotating and V by V greater 0.4, then probably the linear interpolation might not work. So now that for our purposes, what we use is definitely the MESA code, because it has, I don't, for this audience, I don't need to talk about the details of MESA, but then why I specifically like MESA is that it is open code, because anyone can do the experiment with it. And it has a modularity and also the parallelism, although it is OpenMP parallel, not the MPI, but still the parallelism is there, and which is a feature pretty much new to the stellar evolution codes. And for our purposes, what we are trying to see that I'm going to talk about the WNL stars and the different mechanisms that can give rise to this kind of WNL features. And so the first question is like, where do we find this kind of young massive star clusters? Our galactic center has plenty of them, and there are different clusters like arches and quintuplets clusters which have plenty of these massive stars. And initially, when they were detected or they were observed in figure et al, they actually noticed that they are seeing some features which is WNL-like, which is like helium and nitrogen, and they didn't know that term WNL yet. At that time, and also, but at the same time, they have this core which is hydrogen burning, so they are on the main sequence. So these stars were called hydrogen burning Wolfrath stars on the main sequence. But later on, because these stars were renamed as WNL stars, and these kind of stars are also observed in plenty of them are there in LMC. In the 30 Doradus region, in SMC as well, and also the HD 97950 in NGC 3603. So now for this particular talk, our model grade would be a mass grade of 60 to 150 solar mass with mass resolution of 10 solar mass and rotation rate of 0 to 0.6 with a resolution of 0.1. And in this case, we are not using MIST-1, but we are using MIST-2, which is yet to be published, but where we take into account the alpha enhancement at subsolar metallicities, mostly Fe over H less than equal to -1. And that takes into account more realistic kind of abundances. And as you know, that supernova explosions can enhance the alpha elements in the ISM. So we go for the metallicities of solar metallicity, 1/10 and 1/100 of the solar metallicity. Now here to show the results, if you look here in this plot, I'm trying to show the what I'm showing is a surface helium mass fraction, which is shown by this color bar over here as a function of V by V grid and their time evolution. This time scale is normalized to the main sequence lifetime. And as you can see that, the top to bottom panels are increasing stellar masses from 80 to 150 solar masses, and left to right, they are decreasing metallicities. This is solar, 1/10 of solar and 1/100 of solar metallicities. Now you can see that all of these cases actually, when you have rotation rates V by V grid of 0.4 and above, irrespective of their masses and metallicities, all of these cases show WNL kind of features when you have surface helium mass fraction greater than 40%. And the same goes with nitrogen as well. You can see that same goes in the sense like nitrogen enhancement happens. I'm not saying that same mass fraction in nitrogen, but you can see that here I am showing the nitrogen abundances normalized to the initial nitrogen mass fraction. And you can see that the enhancement happens almost of the order of 11 times to 10 to 11 times to almost 30 times, depending on the metallicities and rotation rates. And masses as well. But then the question is like, how do all these heavy elements are being produced within the very central core of the stars, but how does this nucleosynthetic elements get transported to the outer layers or on the surface? So these massive stars we have, if you look into this cartoon picture, we have they have very huge inner convective region, and then there is this radiative layer, and there is this very thin outer convective zone. So inside the inner convective zone, everything is almost convectively mixed, and but then these materials somehow needs to be transported crossing the radiative barrier onto the outer convective zone. And now if you have the rotation as it is pretty these days, it's like rotational mixing is pretty much well known, and if you have the rotation, stars normally gets a little bit flattened, and that's why you see the temperature imbalance between the pole and the equator, and that gives rise to this huge meridional circulation, and that's known as Eddington circulation. And also, if you have the differential rotations and differential velocity distribution or rotation rates, and you can see that if you have there can be shear instabilities wherever there are two different rotation rate zones are coming in contact with each other, be it on the vertical perturbation, and if it is on the vertical perturbation, then you see this GSF kind of instabilities, this is Goldberg-Skubert-Fick instability. And on top of that, if you have the magnetic field, then you see this Spirit-Taylor dynamo-driven mixing as well. So if you have the rotation turned on, here on the right-hand side, what I'm showing is the diffusion coefficient as a function of Lagrangian mass, and for 100 solar mass stars, and at a time when it has lost almost 20 solar mass. And you can see that these two convective zones are actually connected by these different instabilities due to the rotation. But then if you look into the observations, there are observations of WNL-like abundance patterns, but they are slow rotators. But then what are these observations? Like Herrero et al. 2000, they actually looked into 7 galactic O stars, and they found almost 3 of them which shows helium abundances of the order of 35 to 40%, and the projected velocity, which is 100 to 120 kilometers per second, and all of them have mass of the order of 100 solar mass. And also the Harris et al. 1998, they looked into they tried to study the spectropolarimetry of 29 galactic Wolf-Rayet stars, And what you mean by line effect is that, okay, normally how do you measure the rotation rate is that you see these absorption features, and depending on the rotation, you see this broadening, and that's how you measure the rotation rate. But for these kind of stars, you see the emission lines. And now the best way to measure their rotation rate would be the spectropolarimetry, is that you see these emission lines have less scattering compared to the continuums, and you see this difference in their polarization states. And that's what is known as actually the line effect. And if they are really rotating, then you should see a lot of these stars showing the line effect. But what Harris et al. Found that almost 80% show no line effect at all. So that is actually hinting towards probably spherical wind. If they're rotating, you see this asymmetrical wind, but this is probably the spherical wind, and probably that is due to the slow rotation. And now in Vink et al. Yorick's paper 2017, along with Yorick's 2007, Yorick's another paper of 2007, combined observations that is actually 4 stars out of 39 Wolfram stars in LMC. Only 4 stars actually showed line effect. So it's like 10% of what had been observed that shows the line effect. And this is kind of similar to galactic samples as well. This is almost 10%, 10 to 20% that shows the line effect. So there are 2 issues now. So one is like all of these observations are actually saying that there are WNL-like abundance patterns, but they are slow rotators. And also at the same time, if you look at Vink's observations of 2007 and 2017, the weird part of it is that at low metallicity, normally if they are rapid rotators, they can easily maintain high surface rotation rate because weak mass loss, because mass loss is metallicity dependent because of the weak mass loss. And thus more Wolf-Rayet stars actually should show the line effect. However, we are not actually saying that they are observing actually same as what they observe in galactic Wolf-Rayet stars. So it's 10%. So now the question is like, how can we actually have these WNL-like abundances in slow rotators? Because now you don't have this rotational mixing. So after Herrera et al.'s observation came out, George's and Andres' paper came out, and they tried to hypothesis. This is 2000, their paper in 2000, and what they tried to hypothesis is that, okay, what they hypothesized is that, okay, probably these stars are initially fast rotators, and when all the mixing had happened, and now as the stars lose masses, they are also losing their angular momentum, and that's how today they are the slow rotators. But the surface enrichment had happened way in the past when they were fast rotators. So this is
sorry, Arpita. You have a couple of minutes left. If you mind start to wrap up, that would be great.
Okay, thanks. So this is one mechanism that can actually give rise to the surface enhancements, and but if that would have been the case, then we wouldn't have seen the surface enhancement in helium for almost non-rotating stars which are at solar metallicity, but they are massive enough. And that's where comes our new theory of fossil convective cores. And you can see that what we mean by fossil convective cores is that the convective cores that are not today convective, but they were the part of the previous times. And what it does is that as the star is losing mass, it's actually shrinking. As it's shrinking, it's actually kind of showing more and more of its fossil convective zones, or the convective zones of the past times. And that's how you are seeing all these heavy elements on the surface. And here I'm showing a picture or a movie, and I'll probably end with this movie. And you can see that at an initial time, you see that the surface enhancement of the helium mass fraction in the center is 30%, but surface is not yet enhanced to 30%. So at what time we'll see this surface helium to go to 30%? Now I'll play the movie, and you can see that as the star is losing more and more mass, it's shrinking, and it's not yet 30%. But as soon as the current convective zone falls on top of the fossil convective core, we see the surface enhancement, and it's at 30%. So there are similar kind of, I can show another example, but this is the same way that when we'll see the surface enhancement to 40%. And this is another mechanism that can give the surface enhancement for slow rotators or like kind of non-rotating stars if they are metal rich. At least they are metal rich in the sense like F/H is greater than or equal to -1. So here we see these three different kinds of surface enrichment regime, and that's the helium surface mass fraction. One is due to the rotational mixing, and this BC part is due to both rotation, mostly due to this exposure of fossil convective zones, and CD part is mostly the classical Wolf rate phase. And with rotation, you see in this BC part, we have rotation as well as the exposure of the fossil convective cores. So I'll probably leave it at that, and the conclusion would be that yes, there is this mechanism which not only that rotating stars show the WNL-like features, but also the non-rotating or the slow rotators can show the WNL-like features at near solar metallicity, and that physical mechanism which gives rise to this kind of WNL-like features for slow rotators, we call it as exposure of fossil convective cores, and that provides a natural explanation for the origin of slowly rotating WNL stars, and we don't need to invoke the exotic scenarios of stellar spin downs. And I'll probably stop it at that. Thanks.
Thank you, Arpita. Any questions so far? Yeah.
Hi, Arpita. This is Jim Fuller. So in your mechanism, can the mass be lost purely by winds, or does it help to have binary mass transfer enhance the mass loss so that you see the core and more stars?
Yeah, so that's a good question. Yeah, in our case, these are the single stars, which are kind of like, as in the last time discussions, I was also hearing that, yes, these single stars can be like binaries which are not closely interacting. That can be also kind of the single stars. And in these cases, we are seeing primarily due to the mass loss on the main sequence. But yes, binarity would help. That if you have the binarity and the stripping of the outer layers due to the binarity, then you will easily, like more faster in the main sequence, will enter this WNL phase.
Do you think most of the WN stars come from this binary channel, or are mostly coming from just single star wind-driven mass loss?
That's a good question, and for that we need to understand how this WN or Wolf rate to O stars or O star to Wolf rate to O star ratio changes at different metallicity environments, and that's, I don't think, is yet understood well from the observational point of view. But if anyone knows about that in more detail, I'd really like to know about that as well.
Okay, thanks.
Hi, thank you, Arpita. It's Dominic here. So just a comment that as a PhD student at Leuven, so Karen De Silva, who's looking at the binary fraction of WN stars, but Wolf-Rayet stars in general, and a significant number of these are binaries. So I think I'm right in saying about 40%, but I might be wrong on that number. So I agree with Jim that that's an interesting avenue to pursue. My question, so I haven't run a Wolf-Rayet model at 200 solar masses, but in your convective core recession, you have a little bit of a step function. Can you perhaps comment on that, please, and what's causing that?
Oh yeah, I'll go back to, I'll probably share screen again. Yeah. So are you talking about this one? Or this one?
No, in your movie, I think it was.
Ah, okay. Yes, I do.
Yes.
These ones, yes. Yeah, so it is actually, what is happening is, you can see these kind of jiggles, right? So each of the Lagrangian layers, how much amount of time it spends in its fossil convective zones. So you can see that this zone has spent more in the inner fossil convective zone of say 80 when it was at the when the inner convective zone had the mass of 80 solar mass, whereas these parts hadn't spent that much time within the 80 solar mass fossil convective zone. And that's how you see these kind of different steps and ziggles on that. So how much time they are spending into the different fossil convective zones.
So is this a numerical effect, or do we expect this to be physically present?
This is not numerical. This is physically present, because we have also done the resolution test, as Jane was saying, and this is present for all different sorts of temporal and spatial resolutions.
Okay, thanks.
Yeah.
Any other questions? Yeah.
Jamie Tyre, so you talked about helium and nitrogen. Are there other elements that help you, and the ratio or balances of elements that should be present if you're just kind of showing convection zone recession? Is the ratio helpful, and what other elements can you measure?
Yeah, so yes, the ratio is not only just helium and nitrogen, but also the carbon and oxygen. But mostly that is like for the, not for the WNL stars, but or the WN stars, it would be mostly for the WC or WO stars, that where we'll talk about the dominance of oxygen and carbon fractions compared to the helium mass fractions.
Any other short question for the 2 minutes left? Yes.
Yeah, Falk Herrick, thank you for the nice talk. I was wondering about the slightly lower massive stars that would not sort of naturally expose their entire, lose so much mass. And to me, it seems that, also in the 2015, 2025 solar mass range, there is a little bit of a confusion, at least to me. I'm not an expert in neither on massive stellar evolution nor on the observations, but I'm trying to find out whether there's a consensus on the question whether rotation-induced models are reproducing the observed nitrogen and helium abundances, or whether we can distinguish between rotation-induced mixing and the need for maybe other envelope mixing processes. And I think this is something that, if someone has ideas, I would love to discuss, I would love to understand better. But it seems to me perplexing that we can't design stringent observational tests that could settle this question, because obviously it is quite important. I think we agree in low mass stars that there's a problem with angular momentum transport. It seems that observationally we can't determine whether this is also the case for massive stars or not. And so I would like to learn more about that. And so my question to you is, do you have an opinion on that? But maybe it's also a question that other people can comment on.
I don't think that I can completely answer your question, but what I can say that even the mass loss schemes, which I am also interested in knowing, is that there are several different kind of mass loss schemes that are existing in the literature right now for the massive stars. And if we change the mass loss schemes, we see that there is a huge impact on the output, especially the surface helium mass fractions or the nitrogen that I was talking about, that I was recently talking. And this one plot probably says something about it, that if you increase the mass loss, and in MESA, this is by the eta factor, because these are all Dutch mass loss schemes, and you can just simply change them by their strength by eta factor. And if you increase by 3 times what is the default one, and you can see that the surface helium mass fraction actually happens even for metallicities, which is FA over H of 1/10 of solar metallicity, and even for the mass of 80 solar mass. So probably if you go for lower and lower masses, if you have proper mass loss schemes, and I don't know which one is the proper mass loss scheme, and if anyone knows, it would be really good to. I would be really interested in discussing and which mass loss schemes to take into account and which are not, and why, and which will be more observationally matching with observations, etc. And probably if you go for this mass loss schemes where you have higher mass loss, then you can see even for the lower and lower masses, which will also show this kind of surface enrichment due to the exposure of fossil convective pores. That's all I can tell you, but that doesn't answer to your question, I'm sure of that.
Okay, so I think we arrived to the end of the session today. So let's thank Arpita again for a great talk.